Hello, everyone. Thank you so much for having me here. And fingers crossed the presentation works. If not, I'm sorry. So, as you've heard, I'm going to talk a bit about something different, something that maybe you've never heard about, or something that you actually know and you're interested in. So, we'll find out. I'm going to talk about the DART and Hera missions, and planetary defense missions, and why we need planetary defense. Because you might not think about it. And I'll start off by telling you how awesome asteroids are. They are absolutely great. Many of you, when you look at them, you might think, okay, it's a rock, it's gray, right? But just look at all of these beautiful, beautiful rocks. They come in all shapes, all forms, all sizes. And I really like this figure here because it just shows how far we got and how many amazing, amazing space missions we had in the last 25 years. The science of asteroids was completely revolutionized in just 25 years. So everything is very, very new. And we had some really good ones. You might actually have heard of some of them. You might have heard of Rosetta, for example. If you're from Bern, some people in Bern work on this, or worked. You might have heard of the Dawn mission that went to asteroids Vesta and Ceres. Or more recently, the Hayabusa 2, OSIRIS-REx missions brought samples to Earth. Cassini, maybe you've heard of Cassini. So really, really good, great, and very successful space missions. But the thing is, every time we go to an asteroid, we are completely surprised. We don't actually know what we find before we go there, because they are so far away that from Earth, we can't see them. So we need to go there and actually look at them. And what we found, every time we go to an asteroid, we find really amazing and fascinating things, like really fascinating geology, like craters and boulders and lineaments, and a lot of geological features that you do not have on Earth. And by studying how these asteroids formed, we can also understand how our own solar system formed, how Earth formed, how material was delivered to Earth, and maybe how even life began. And while we had some really, really great space missions in the last 25 years, now we are in the golden age of asteroid exploration. Over the next 10 years, we are going to go to more than 10 new asteroids. So we had, for example, just a few years ago, we had the Hayabusa 2 mission. This is a Japanese space mission, which was a complete success. It went to asteroid Ryugu. And this, you can see here, asteroid Ryugu is about 900 meters in diameter asteroid with a very, very low density, and which means like a high porosity. And you can see there are just rocks everywhere. But why this space mission was special is because it had what we call an artificial impact experiment. And this is it. It's called the Small Carrion Impactor. It went to the asteroid, and it impacted the asteroid surface. Here. And it created a crater. So it was a 2-kilogram copper impactor at 2 kilometers a second, and it formed a crater. And these are images of the crater evolution. Try to show it again. Maybe it's hard to see from the back, but you can clearly see ejecta coming out and forming a crater. There you go. And it was very interesting because the projectile wasn't very large. So 2-kilogram copper projectile, not very large. But the crater that it made was 14 meters across. Huge, huge crater, which was not expected. So again, we were surprised. But using numerical models, we were able to reproduce this. And what it told us is that the surface has very little resistance, that material just moves away, which we don't have that much on Earth. This mission was great because it was also a sample return mission. So this is It had an arm that went to the surface to collect samples. And these samples are now back on Earth, and they are being studied all over the world. They are also in Switzerland at ETH Zurich. They have a few grains that are studying there. So this is the sample, you see, but that is 5 millimeter. So it's very, very tiny grains that are being studied. Another great space mission is NASA's Lucy mission. It was launched in October 2021, and it's going to study the Jupiter's Trojans for the first time. It's on a 12-year journey, and it's going to look at more than 10 asteroids. That's a huge number. You might have heard of NASA's Psyche mission. It was launched last year. And it will visit asteroid 16 Psyche, which is believed to be the exposed core of a protoplanet, which again is incredible because on Earth, we can't really study the Earth core because it's so deep down. But if it's an exposed core just there in space, it just waits for us to go there to see what we find. So asteroids are absolutely great, but we also care about them because they might one day be a threat to Earth. So here it shows a graph of the number of impactors in diameter and how often they would fall on Earth. And you can see that the asteroids of the same magnitude as Chicxulub, and you might know Chicxulub is the asteroid impact that is believed to have led to the extinction of dinosaurs. But you see that they are very, very rare. So the good news is that it's very unlikely that we have to worry about a mass event, extinction, dinosaur killer event. However, in more recent history, we had two quite large events. Maybe you remember the Chelyabinsk. It was in 2013, where a 20-meter asteroid exploded above the city of Chelyabinsk. And it created quite a lot of damage. So here in the corner is a factory that collapsed because of the explosion. And then in the early 1900s, another asteroid exploded above Tunguska, which was lucky enough that it was in Siberia, and there were many casualties because not many people lived there. But it just flattened kilometers and kilometers of forest. So if such an event, if an asteroid would come towards a city like London, New York, maybe Zurich, what, are we just going to let it fall? We need a plan, right? And we know that these events do happen. So this is a map of all the recorded asteroid entries that produce these fireballs. In the last, what's that, 40 years, 30, 40 years? 30 years. And you can see they happen everywhere. So it's not a question of if, but when. The big one there is Chelyabinsk. So here are some numbers. So as I said, the very large total disruption events, we don't have to worry about them. They are very rare. We characterized most of these bodies in the solar system, so more than 95% of them, and we know we are safe from total disruption. The very, very small ones, about few meters, they happen every year, but we are safe from them. They just disintegrate in the atmosphere. They don't cause any damage. But we have to worry about these bodies between about 25 and 160 meters, because they are hard to spot, being so small. And if they explode in the atmosphere, or if they actually reach the ground and make an impact, they could have devastating consequences if there's a city nearby. And as you can see, we discovered less than half of them. So there are many, many of these bodies out there that we might only see them coming at the last minute, or only a few years in advance. But if we do see them coming, and we know they are there and they might cause damage, we need to have a plan. How do we deal with it? And there are several ways. If we discover them very, very far in advance, There is a concept that is called the gravity tractor. You basically send a spacecraft out there that is going to orbit the asteroid and slowly move, very slowly, move it away. It's an easy concept. It doesn't need much technology or whatever, but it's very inefficient. It relies on the gravity of the satellite. So you have to wait a very, very long time, like decades, maybe 100 years, to know if it was efficient. If the asteroid is very big, or you don't have you don't have a lot of warning time, of course, there's the nuclear explosion. You might have seen Armageddon. It's highly efficient. You basically destroy the asteroid. However, it's not the desired solution. You have very little control, and it's potentially dangerous. So, if possible, you want to avoid nuclear. Really, avoid nuclear. But then there is another method, and this seems to be the most straightforward solution with not so many disadvantages. And it's called a kinetic impactor. And okay, this is what DART and Hera missions are all about. So if an asteroid comes towards Earth, this is not a one country's problem, but it concerns all of us. And that's why you have the AIDA International Collaboration for Planetary Defense. It is made of 2 space missions. Is NASA's DART mission that was in 2022, so only a couple of years ago. And it's also, from the European side, the European Space Agency's Hera mission, which I'm going to talk more. But let's start with DART. So DART was a kinetic impactor test. It went to this binary system called Didymos. That is the main asteroid. And it impacted the little moon, which is called Dimorphos. You can see it orbiting. And before the impact, it ejected a CubeSat called Licia Cube that witnessed the event. And as a result of the impact, it managed to change the orbital trajectory of the moon, which is basically, you can see there, from the original orbit to the new orbit, basically it shrinked the orbit. A bit about Didymos, so the system. We didn't always know it was there, so its discovery is quite recent. So these are some images from its discovery. Can you guess where it is? Yeah, it's right there. So it's literally a dot. But these are the first images when this system was seen and discovered. To give you a scale, so the primary Didymos, it's about 800 meters in diameter. It's a bit larger than the Tokyo Tower. However, the moon, it's much smaller. It's about 160 meters across, so it's about the same size as the Great Pyramids. The DART spacecraft, it's even smaller. It's about 90 meters, so it's about the size of a bus. So impacted a bus into the Great Pyramids. This is the spacecraft in the lab. You can see it's about the size of a, yeah. So this is with the panels rolled up. You can see here the solar panels, they are rolled up. So with the panels rolled up is about the size of a vending machine. And this is being integrated into the SpaceX Falcon 9. This is in 2021, so it was launched in 2021 from the Vandenberg Space Force base. And you can see it there being very, very tiny in this kind of rocket head. And these are some really nice images from the launch. Apparently, the launch was fantastic. Unfortunately, it was still pandemic, so I couldn't go. And these are the last images ever to be seen of the spacecraft. These are from the rocket as the spacecraft was deployed, and basically going to the space and saying goodbye. And then fast forward to September 26, 2022. The impact happened. The impact was broadcasted live on the NASA channel. Okay, there you go. So everyone was watching. And these are some of the final images that were seen live. So you can, this is where we saw for the first time the system. So you can see there in the corner, that is the primary Didymos. And these are the last images just before the impact. And you can see people in the control room being very, very happy. And as the impact was confirmed, so impact confirmed. Yeah. And you can see people don't hug. It was still the pandemic. So 2022. But yeah, it was great. Yeah, we impacted an asteroid in space. So as I said, these are the last few images. So from the spacecraft, we didn't see the asteroid until about 4 hours before the impact. So 4 hours before the impact, the bigger asteroid, the primary, was 1 pixel. Until then, it was not seen from the spacecraft, so it was just programmed to go in the right direction. But as soon as it was seen, the spacecraft was autonomously driven. So that the computer was programmed to, as soon as it sees the asteroid, to lock on it and to target it. This could not be done manually because this spacecraft was traveling at 6 kilometers a second, so extremely fast. And then if you also account for the delay in where the spacecraft is and by the time you reach the data on Earth. So the computer did all the work. And then only about 1 hour before the impact, it started to see the actual target, which was 2 pixels. Then, about 2.5 minutes before the impact, it saw is the final image where you had both asteroids in the same field of view. And then just 2 seconds before the impact, it transmitted the last complete image, and you can see the impact site. It went straight for those big boulders in the middle. Here, some zoom out. So this is the last image with both asteroids. So the big guy and then the actual target. This is the last image where you have the whole target in the field of view. And this is the last few images. And the final image where it's just a bit because it crashed before it managed to send more. And here is a nice animation that shows you just how it went for those boulders, just in the middle. So you see there before the impact, and as I mentioned earlier, there was a CubeSat to witness the event. And these are the images that were returned by the CubeSat. So this is the main asteroid, and then you can see faintly that's the actual target, but you can see lots of stuff coming out of it. Let's try again. So the CubeSat was also traveling very fast. So it captured these images as it was traveling also at 6 kilometers a second. And you can see here lots of material coming out. But this material coming out, it was observed from all over the world, literally from all continents, but also from space. It was also imaged by the Hubble Space Telescope, by the James Webb, but also from the Lucy mission. So another mission was also looking at DART. So everyone was watching. And the results did not disappoint. So these are some first images just 12 minutes after the impact. That is from Hubble. So you can see some material coming out as an ejecta. This is from JWST. JWST at that time was pretty new, so the calibration is a bit worse than Hubble, because technically it should have been better. Now it's better. This is 2 days post-impact. So the impact came from this direction. You can see the ejecta. But something else you can see that the system started developing a tail. And this is basically material that was swept away by solar radiation pressure, a bit like in a comet. So basically, we made out of this asteroid, we made a comet. This is 12 days post-impact from Hubble. You can see the ejecta starts being swept away and further develop the tail. This is 52 days post-impact. Now it has a very long tail. This is what? 120 days post-impact. Still has a tail, very faint, but it's still there. 168 days before impact. You can, again, see the tail. And this is the last image we got, which is about between 276 and 282 days post-impact. And it was the last time we managed to image the system before it went into an area of the sky that is not observable from Earth. But you can see, the last time we saw it, it still had this large, large tail. OK, so we impacted the asteroid. But the aim was to deflect it, to see if we can deflect an asteroid in space. And we chose a binary system for a reason. It's because it's much easier to measure if we manage to deflect it, as opposed if it was just a very tiny asteroid in space, then that we can barely observe. But this way, by looking at the larger asteroid, we can look at its eclipses, and this way measure the trajectory of the smaller body. Here on that side, you can see the observations just after the DART impact. It basically shows you the brightness coming from the system as a function of time. And where there is a tip, it means there is an eclipse. So the light is obscured. It works pretty much like the eclipses you have on Earth. So it was observed at 11 hours and 23 minutes, but it was expected to have the dip at 11 hours and 55 minutes. Which means that the impact was highly, highly successful, and it changed the orbit by more than half an hour, which is really, really huge, because we were expecting to have a few seconds difference. So half an hour is a lot. And that means that the impact was highly, highly effective at deflecting this asteroid. We also observed it in radar. So you have here the radar images shortly after the impact. So here is Didymos. Can you see Dimorphos? Me neither. OK, this is very faint, but that's Dimorphos there. Oh, and the other one is where it was expected to be found. Yeah, this is very, very faint, but it's there, which was great, because so being in the Science Operations Center after the impact, we saw these images coming in from the observers all over the world, and we saw so much ejecta going on everywhere. So for a very short time there, we were wondering, is the asteroid still there? Well, it was imaging radar. It's still there. We didn't destroy it, but definitely made a big boom. So DART had several level 1 requirements. The first one was to impact Dimorphos, which it did successfully, right in the middle. It was to change the binary orbit of Dimorphos by more than 73 seconds, which it did. It changed it by more than half an hour. So it massively, it was highly, highly successful. The number 3 was to measure this period, which we measured from all observatories and in radar. But then the last requirement was to characterize what is called the beta. So how efficient is this technique, kinetic impactor technique? If we go to another asteroid, what should we expect? So first of all, how does this whole kinetic impactor business work? And it's actually not that, it's actually quite straightforward. It's about conservation of momentum. So if you have mass m, so let's say the spacecraft, impacting a target with the mass capital M, and it's a simple inelastic collision, then the change of velocity of the target is just the momentum of the impact divided by the mass of the target. However, in the case of an asteroid impact, things are slightly more complicated, because from the impact, there is a lot of ejecta coming out. And this ejecta carries out an additional momentum. And this additional momentum acts as an extra push to the asteroid. So it's a bit like, if you may, like a thruster for a rocket. So it gives an extra push. But this extra push we quantify by a value that we call beta. So basically, if this beta is 1, then there's very little ejecta, very little deflection. If there is 2, it's moderate, and a moderate increase. Then if it's 4, then it's a lot. For the dart impact, actually, we don't actually know this beta. So it could be anywhere between 2 and 4. And that is because despite the fact that we know the impact conditions, so we know how the spacecraft looked like, we know its velocity, we know where it hit, we have images of the asteroid. However, the spacecraft was going so fast that just from the images, we are not able to say much about the target. We're not able to say what is the mass of the target, which is essential because to calculate the momentum. We don't know about its internal structure. We don't know its bulk density, porosity, and all of these things, they affect this momentum efficiency. However, if we look at it, it looks quite similar to previous asteroids that we went to. So, for example, there was Ryugu, was the asteroid that was impacted by the Japanese mission that created the crater. There's Bennu, very similar to Ryugu. And this is Dimorphos. And it looks like what we call a rubble pile. Basically, a conglomerate of rocks that are held together by very, very little forces. Basically, a rubble pile. So what we did in Bern, actually, at the University of Bern, we used numerical simulations to learn more about this impact and what it tells us. We used all the information that we knew, such as the shape of the asteroid, the impact site characterization. So the shape is there. It's this oblate spheroid. It looks a bit like an M&M candy. The impact location with those very large 3 boulders, and then the X there, it shows the impact location. So it was, as I said, straight in the middle of those boulders. And we constructed numerical simulations using all of these conditions to see what happened, and if we can say anything about the target. And we compared the results with the ejecta that we saw coming out from the impact. So right there is an image taken by the Licia cubes, so the CubeSat. You can see it goes like this. You can see it's a lot of ejecta. Here is a zoom in of the ejecta. And here is the numerical simulation that best matches the outcome. And what we found was that Dimorphos is also very, very weak, with what we call the cohesion of less than 1 Pascal, or a few Pascal. So cohesion, if you think about it, if you think of flour, the flour you make you use to make cakes, flour has a cohesion of a few 100 pascals. Sand, on the other hand, has almost no cohesion. So the target is very similar to a conglomerate of rocks and sand-like material, but in space. However, for such a weak target, what it means that the DART impact did not actually create a crater, as in the case of the SCI impact, and as it was expected, but instead it deformed the asteroid. It caused a global deformation. And you have here a simulation showing the ejecta growing and the deformation of the asteroid. And there it shows the shape of the asteroid before and after the impact. And you can see there's a chunk that has been redistributed on the target. So about 2% of the asteroid's mass was ejected into space, but up to 18% of the mass was redistributed on the target, which means that now Dimorphos is very likely has a very different shape than it had before the DART impact. But if we'd stop here, that is pretty much all we could say, because DART spacecraft that doesn't exist anymore, got disintegrated. We had images from the Earth. But this seems like DART was a large experiment in space. So we did the experiment, but now we need someone to go there and see what happened. And this is where the European Space Agency comes in. And the Hera mission. So Hera mission is launching very, very soon in, I think, just over 3 weeks. It is going to go at the system to see exactly what happened. It's launching from Florida on a SpaceX rocket. It's going to fly for about 2.3 years. And it will arrive at the system in early 2027, where it's going to spend 6 months to characterize the system and to see exactly what happened, to have a complete image of this large-scale experiment in space. So the Hera spacecraft has several payloads. It has a camera to image what happened. It has a LiDAR. Has a thermal infrared imager to look at the material properties on the surface. A hyperspectral imager to look at the composition of the surface, but also has 2 CubeSats called Juventas and Milani. One of them is going to soft land on the surface to see what happens. Is it going to jump? Is it going to sink? We'll see. So here is actually a cool image that I added recently. So this is the backbone of the spacecraft, this tube. And it was actually built in Bern by RUAG Space. OK, so one of the measurements of Hera is to measure the mass of Dimorphos. And it's going to do that by measuring the wobble. And this is going to tell us what the efficiency of the impact was. Another aim is to measure the dynamics. And one of these is called the libration. It's basically how the satellite moves around the primary. And we have similar movements for the moon. But also to see exactly what happened, and which is going to give us an opportunity to verify these impact models. So the Hera spacecraft, this is the Hera spacecraft in the lab on August 8th. These are the solar panels, and that black thing is the body. But it was on the move, so this is just 1st of September. As is being transported from ISA ESTEC in the Netherlands, where it was the final integration, to Florida, where it is now just having the final test and being integrated on the rocket to launch in less than 3 weeks. So, asteroids are great. They are really, really lovely. You should look at images of asteroids. That was a complete success. It impacted the asteroid. It made a really big boom. It showed us that we can actually deflect an asteroid in space. And Hera is fascinating. It's going to be the first rendezvous with a binary asteroid system. And it's going to give us a complete characterization of what happened and document this large experiment in space. And the launch is in about 3 weeks, in October 7th, at, what is this, 4:52 Central East Time. And you can watch it live. So if you Google it now, watch Hera launch, it's going to take you to YouTube of the NASA spaceflight. And if you go there at this time, that's all on Google, you can find this information. You can watch the launch live. So, yeah. Thank you. I hope now you're more interested in asteroids, and thank you for listening.
Thank you so much, Sabine. Do we have any questions for Sabine? Back there? OK, we'll do a multi-stage launch. Can you please toss the cube back there?
That did not go well.
That was a failed launch.
Also, if you want stickers, find me after. And if you have more questions, you'll get a sticker.
Thank you. So I was going to ask about Hera. You talked about all the amazing instruments that Hera has. Do we have comparison data from before? Because like if we have like once it arrives, spectral imaging and like the thermal stuff and such, do we have data from before?
So we only have, so DART spacecraft only had a camera. So we have those images to compare. It's still something. It's still better than nothing. However, it is expected that while Dimorphos got kind of reshaped, the main body, Didymos, still has places that are primordial, that were not affected by the impact, that can be used for comparison.
I see.
Thank you. I think we had other questions over here.
Maybe you know, how do we navigate towards such a distance object when we cannot even see it with the camera?
So the trick is that people are using observations to characterize the trajectories of these small bodies, and they are using repetitive observations over years and years in such way that at the end they have this trajectory with very high accuracy. So then, even if you don't see the target, you see where it is located in space, or where it will be located in space if you propagate the trajectory. And that way, you tell it where to go, and then as soon as you go close enough, so in the case of the DART impact 4 hours before the impact, you have a navigation system that tries to find the target and lock on it to do the final maneuver.
Thanks.
Thank you. Another one. I'm glad I'm not the only one.
Yeah, so what is the likelihood if you interact with these asteroids that you actually impact it in a way that the trajectory will then change and target Earth? Or is this even considered as an option?
If this asteroid would be just in space, not in a binary system, you'd basically have to impact it in the opposite direction to have the opposite effect. So it's quite hard because it'd be the opposite direction. So you do calculate the trajectory beforehand. It's difficult. It would have to turn around, which is not possible.
Thank you for that important question.
Just to be safe, you know.
No, they're definitely not possible.
Sorry, maybe something in a similar vein. How sure were you that the impact was going to push it towards the larger object and not away from it? Is just the fact it's coming from the outside, or
No, so the secondary was rotating around the primary in a certain direction. If you impact it opposite to the direction of movement, then it slows down, which is what it did. By slowing down, you basically go inwards. If it was impacting from the opposite direction, it was giving an extra push, making it faster, move outwards. So it's basically the direction from which you come.
okay, but you weren't sure which direction it was going to, or
You-
DART
you-
wasn't
you
sure.
You knew in which direction it moves.
Are they in which it moves? But
Yeah.
did they also know in which direction it would push? In that
I mean,
case?
you know from which direction you're coming.
Ah, okay. Yeah. Thank you.
We have time for one last question. Over here.
Really nice presentation. Why is a nuclear explosion such a bad idea? Why is it so dangerous? I mean, it's so far away, so why? I mean, it looks like the most obvious solution to me.
The list of reasons is actually very long, but the most obvious ones is if the launch is a fail, you have a nuclear thing exploding at the launch pad. You don't want that. It's hard to control it, right? So let's say the launch is successful, but you make it explode near the asteroid. It's hard to control it, to control where the energy goes. You might end up just destroying the asteroid.
A problem,
Which
right?
Instead of having one asteroid that is coming towards Earth, you have 1,000.
Okay. Thank you very much.